In our fourth and final video, we will be using the Glassboro interpretation to ultimately resolve the Afshar experiment paradox.
To quantify wave-particle duality, we introduce two parameters, a particle parameter k, which-way information, and a wave parameter v, visibility.
The which-way information measures the degree to which we can identify the origin of a particle. For instance, consider a particle that comes from one of two sources. When either of the two detectors trigger, we know that the particle was on its corresponding beam from the source, and therefore we have maximum which-way information of 1. When we cannot identify the source, we have 0 which-way information. We may also have partial which-way information between 0 and 1.
The visibility measures the contrast between bright and dark fringes in an interference pattern formed by accumulation of particles. Thus, if we determine that a particle always avoids a given region, then its visibility is maximum, 1, since this region is a dark fringe. On the other hand, when a particle is equally likely to reach any place within a region, then its visibility is 0, since it reflects in a uniform distribution. We also can have partial visibility between 0 and 1.
We see here two beams with 0-point fields that cross and end at detectors. At the beam intersection, the fields show a region of sharp constructive and destructive interference with visibility equal to 1.
Due to momentum conservation, free particles travel in a straight line. Therefore, when an end detector triggers, we know the source that originated that particle. This results in which-way information of 1. Since the field shows interference fringes with visibility 1, we seem to have a violation of the inequality. However, according to the Glassboro interpretation, the particle is the carrier of energy momentum. Thus, only particles can be experimentally measured. This implies that parameters k and v do not apply to the field, but to the particle only.
The 0-point fields do not transfer momentum to move particles out of dark fringes and towards bright fringes. Thus, the particle maintains a uniform distribution within the beam with 0 visibility. There is no violation of the inequality.
Particles approach the screen moving in straight lines and uniformly distributed within the beam. However, close to the screen, photons must be deflected away from dark fringes and towards bright fringes. The force necessary for this deflection is not likely to be electromagnetic, since electromagnetic force would be too small to deflect a photon that quickly. This force is likely new, a strong force similar to the force that keeps two identical fermions from taking the same state.
According to the Glassboro interpretation, if the conservation laws are fulfilled, then field directives are obeyed. In this case, the macroscopic screen must provide transverse momentum to the incoming photons so that they may form constructive and destructive interference fringes. At the screen, the particle visibility is maximum. However, we do not know the origin of each particle that hits the screen.
A thin wire is scanned across the beam intersection, showing the presence of an interference pattern. This graph shows decrease in photon count as a function of wire position. When the wire is at the center of a dark fringe, there is practically no decrease in photon count. When the wire is at the center of a bright fringe, the decrease is as large as 12%. This is evidence of an interference pattern with visibility close to 1.
A wire is at the center of a dark fringe. Photons that miss the wire just go straight through. These particles have full which-way information, but no visibility, since they ignore the interference fringes. However, a photon that would hit the wire somehow makes a sharp reflection around the wire and then continues straight, maintaining its high which-way information. Since the photon avoids the wire, its visibility is maximum. This photon violates the inequality.
The Afshar experiment makes the situation worse. Here, a wire grid is placed at the center of dark fringes. Experimental work done at Rowan University shows that when the wire grid is at the center of dark fringes, the decrease in photon count is minimal. Particles act as if the wire grid were absent. Thus, the visibility is large. From diffraction calculation, it appears that most particles go straight through as diffraction is very small. Thus, the which-way information is large and the violation of the inequality is large.
Among proposed solutions, we find only partial answers here.
There are two identical momentum states available to the outgoing photon. The photon may take either state provided that the photon obtains transverse momentum from the wire necessary for deflection. Now, when an end detector triggers, we do not know if the photon originated in source 1 or 2, and the which way information is 0. Thus, there is no violation of the complementarity inequality.
The wire is at the center of a dark fringe. Particles that miss the wire go straight through. Particles that would hit the wire go around and then randomly go straight or deflect to the other beam. This is a 50-50 effect. We may call the interaction of the photon and the wire quantum scattering, since it is not due to an electrodynamic interaction. Electromagnetic interaction only produces minor diffraction.
Since particles avoid the wire, their visibility is 1. Since particles randomly go to one end detector or another, the which way information is 0. Therefore, there is no violation of the complementarity inequality, and the Afshar experiment paradox has been solved for the first time.